Hello aviators. Let's talk about navigation systems and charts. Well before the dawn of GPS, pilots relied on radio-based navigation, pilotage, and dead reckoning. These systems included the likes of NDBs, VORs, DMEs, and localizers, many of which are still in use today. The Very High Frequency Omnidirectional Range, known as VOR, is a radio-based navigation system introduced in the 1950s. It works by sending out 360 radio signals, one for every compass degree. When distance measuring equipment, known as DME, is installed, the VOR is referred to as VOR DME. Also, when military tactical air navigation equipment is installed, the VOR is referred to as a VORTAC. Accordingly, both VOR DME and VORTACs provide distance to the station in addition to course information. Now let's talk about how to use the VOR. The courses from a VOR are referred to as radials. Radials are always coming from the station. The VOR indicator, or course deviation indicator, CDI, can be rotated to track a specific radial to or from the station. Also, the receiver has both a to and from flag. Now when you have a centered needle and a to indication, it means that the radial is on the bottom of the compass card and course to the station at the top. On the other hand, with a centered needle and a from indication, the radial and the course are both at the top of the compass card. There are two different ways to identify a VOR, either by a voice signal or a Morse code. The VOR consists of a VOR ground station, automatic monitoring system, antennas, and a standby transmitter, which turns on when the primary transmitter fails. Also, your VOR receiver must be checked within the preceding 30 days in order to be used for IFR flight, and that's according to CFR 91.171. This can be done with various VOR checks, for example, an airborne checkpoint, VOT, or dual VOR receivers. Let's talk about each one of them. First, the VOR receiver can be checked over a designated aerial checkpoint and must indicate within 6 degrees of the selected radial. Second will be a VOT, which is a ground-based VOR test. The VOT locations published in the chart supplement transmit a series of dots or a continuous tone. Now to use a VOT, 108.0 must be tuned into the receiver with the CDI centered on 0 degrees. The to from indicator should indicate 0 from the station, or 180 with a to indication. The needle must center within 4 degrees of that selected radial. And finally comes the dual VOR receiver check, in which CDIs, the needles must center within 4 degrees of each other. Now let's move on to something much more advanced, much more fun, which is Global Positioning System, known as GPS. GNSS, or Global Navigation Satellite System, is a group of satellites that transmit a high power signal containing time and distance information. 3 systems exist: the Global Positioning System, the US-based system that is, GLONASS, the Russian GNSS system, as well as Galileo, the European GNSS system. Currently, India is also bringing a GPS system online. A GPS is a series of 30 satellites orbiting the Earth. These satellites are placed in various orbits to ensure that at any given time there are at least 8 satellites in view. Each satellite, when picked up by a receiver, places that receiver or your aircraft in a circle. That circle tightens for each additional satellite, leading to a precise position. Now, 3 satellites can do the job, but without accurate altitude information, which is an essential ingredient for GPS approach capability. So, for GPS to be approved for terminal or approach operations, the system must be baro-aided or have a 4th satellite. There are two types of systems used to maintain or monitor GPS accuracy. These are the RAIM, or Receiver Autonomous Integrity Monitoring, and WAAS, Wide Area Augmentation System. RAIM works by adding a fifth satellite to the mix, or baro aiding, which mainly can detect an issue with the integrity of the system by checking for a faulty signal and then displaying an error message if one is detected. WAAS works by utilizing a series of ground stations that receive GPS satellite signals and correct them for time corrections. Let me explain that. Each satellite has an atomic clock, but due to distance of signal and position, each satellite may be off by a second or two from another satellite. The WAAS ground stations correct this error. This correction is then transmitted to a geostationary satellite, which then transmits the signal to WAAS receivers in your airplane. One of the most important functions of GPS is that it allows a pilot to fly a more direct route that may not have been possible before with radio navigation. This can save time, fuel, and money, making flight operations much more efficient and faster. Now let's talk about some important GPS features. The Direct To button on a GPS unit is a great feature for the pilot. It's used for direct IFR or VFR navigation. The pilot simply inputs a destination identifier, executes the function, and the GPS provides a course to fly and distance to that airport or waypoint. Another great function is the Nearest button, which always displays the nearest airports to the aircraft's position along with relative bearings. This can be especially useful to a pilot in an emergency situation or an unplanned diversion. It allows you as a pilot to quickly get headed towards the closest airport. Also, it is very important that a pilot knows how to operate the GPS unit on their aircraft. It can increase flight safety and efficiency of operations. Let's name some examples, like a reroute on an IFR flight, a shortcut issued by ATC, looking up a frequency for a nearby VOR, or switching between the GPS mode and VLOC. They're all functions a pilot should know how to quickly access and use. Also, the pilot should ensure the GPS unit is approved for the type of flight to be conducted, determine that the GPS databases are current, and the route is properly programmed. All right. Now, two terms you'll hear a lot about when it comes to flight planning are pilotage and dead reckoning. What is pilotage? It's defined as navigating by reference to landmarks or checkpoints, and it's most commonly used with either dead reckoning and or radio-based navigation. When selecting checkpoints for a flight, a pilot must pick prominent landmarks that are readily seen from the air. This includes roads, rivers, railroad tracks, lakes, power lines, and or airports. Also, the pilot should not rely on a single checkpoint, as this may increase the chance the pilot will become lost. A bad example for a checkpoint is towers or antennas. These really are hard to see, and many exist that are not charted, which can confuse and mislead a pilot to a false sense of location. In addition, if the pilot flies low to see the checkpoint, they risk a collision with the landmark itself or the surrounding terrain. Now let's talk about dead reckoning. It is defined as navigation solely by means of computed time, distance, airspeed, and direction. Dead reckoning is commonly used along with pilotage on cross-country flights unless that flight is over water. All right, aviators, now let's talk about sectional charts, which is the old man's way for navigating around in the skies, the good old Dave way. Sectional charts are a commonly used chart by pilots for VFR purposes. These charts provide such information as airport data, navigational aids, airspace, and topography. The chart also includes a chart legend that will help the pilot interpret most all the information and symbols on that chart. In addition, ATC frequencies and information on special use airspace are listed either on the chart or on the border panels. Now, blue versus magenta airports. When an airport symbol is a blue color, it has either a full-time or part-time air traffic control tower. All other airports, including non-towered airports, are displayed with a magenta airport symbol. Lines of latitude and longitude are displayed on the chart and are used to calculate and plot a true course. They form a grid system on the chart, and you'll see within each grid a group of two numbers written in blue. These numbers indicate the maximum elevation figure, or MEF, for that grid. The MEF depicts the lowest altitude you can fly and still be assured to clear every obstacle within that quadrant. Now, in determining the MEF for a man-made obstacle, it's done by taking the obstacle height and adding 100 feet, then rounding up to the next 100-foot interval. For example, the tallest tower in a particular quadrant reaches 2,045 feet MSL. Add 100 feet and then round up. The MEF for that quadrant would be 2,200 feet. Another feature of note is that non-ICAO recognized airports will typically have a number in the identifier, such as 1T8. Airports identified by ICAO will typically be all letters and be preceded by a K, such as KSAT. Now let's discuss a few airport symbols. When an airport symbol displays PVT on its symbol, it means that the field is a private airfield. When an airport symbol is marked by an X, then the field is abandoned, but it's been left on the chart because it has a use as a navigational landmark. Keep in mind that the amount and direction of the Earth's magnetic variation will vary by time and location. To display this, the sectional chart contains broken magenta lines called isogonic lines. Now, to convert a true course on the chart to magnetic, the pilot must use the nearest isogonic line. For example, if the variation is 4 degrees east, the pilot would subtract 4 degrees from the true course. An old phrase that helps us remember to subtract east variation and add west variation is, east is least and west is best. Now, let's talk about the different types of airspaces. Class A airspace from flight level 180 to flight level 600 is the only airspace not displayed on sectional charts. Class B, Bravo airspace, is displayed by a solid blue line. Class C, Charlie airspace, is displayed by a solid magenta line. And Class D airspace, Delta, is displayed by a dashed blue line on your sectional chart. Class E, Echo airspace, is that airspace above Class G, or Golf, with a floor of 1,200 feet AGL that laterally abuts Class G, and that's defined by a blue vignette. Class G airspace, with a ceiling of 700 feet AGL, is displayed within a magenta vignette. The Class G airspace with a ceiling of 1,200 feet AGL is displayed outside of the magenta vignettes. A TERSA, or Terminal Radar Service Area, is displayed by a solid gray line on aeronautical charts. Other types of airspace, such as the Special Use Airspace, or SUAs, use special markings to designate their boundaries. MOA, or Military Operation Areas, and Alert Areas are defined by a magenta comb symbol. Warning, Restricted, and Prohibited Areas are defined by a blue comb symbol. Military training routes are defined by a solid gray line with the name of the route displayed in black symbols. The chart supplement is a separate book that includes information for pilots intended for use during the flight planning process and during the flight. The communications section displays a variety of radio frequencies the pilot may use, such as frequencies for the airport tower, approach or departure control, if applicable, ground control, and flight service frequencies. The navigation section displays usable navigation aids at or near the airport, such as VORs or NDBs. The runway section displays available runways, runway distance, landing distance available, and grades. The remarks section will display a variety of information. This will include such items as wildlife warnings, fuel type and availability, parachuting and soaring information, and special conditions such as non-standard airport markings. Hotspots will also be noted in the chart supplement. Hotspots are places of possible aircraft collision and/or runway incursions.